please do not try what you are about to see at home.
Well, there's your problem.
In this special series of MythBusters,
Almost too exciting.
the Dream Team tackles their dream themes.
It's scientific!
Testing myths about everything from electricity to pressure and gravity.
This one hurt a bit.
Shaking down the science of shockwaves, velocity, and impact. With crazy chemistry,
Oh my goodness.
far-out physics,
Fun for the whole family.
and insane explosions.
Is everybody okay?
Life's burning questions answered. On MythBusters, there's your problem. In this episode, the MythBusters fire up the front burner to investigate the science of heat. Then they turn the dial way down for a frosty foray into all things frozen. They're colorful, they're delicious, and they're fun.
Are we doing an experiment here, or are we screwing around?
But when they heat up, these bliss balls have been known to blow up, causing serious burns.
The exploding jawbreaker. We know this happened, we just don't know why.
Yeah, we have the police reports and everything.
What could turn a jawbreaker into a potential bomb? This complex candy starts life as a small, solid center. Then sugar syrup is applied layer by layer in a process that takes 5 days. And that could be key to their explosive potential.
That's pretty. The first thing that I noticed when I cut this open is that there's a potential for a temperature differential.
A temperature differential means a layer inside the jawbreaker could heat more rapidly than the outer shell. The layer would then expand, creating internal pressure and instability. If somebody nibbled on a jawbreaker in this state, it could burst open, releasing its scalding hot interior.
With the slightest, messing with it, it would go off like a bomb.
So the team wants to come up with a heating and cooling regime to determine which scenario, if any, would make the jawbreaker explode under pressure.
Smells really good.
Look at that.
God, look at that. There's a hole right in the side of it.
Don't try this at home.
Going hot. Nope, nothing explosive there.
No one wants a scalded mouth. So Adam's come up with a snappy plan.
We have to build a fake mouth to chew on a gobstopper.
Okay.
We want it to be able to chew, which means the lower jaw will be the hinged part. The upper jaw will be fixed.
Okay.
Like in the head.
Let's hope Adam's granny doesn't miss her dentures, because Tori's going to apply some serious bite force.
What I've done is I've hooked up this force gauge to this device, and this will give us an accurate reading of how much the jaw exerts.
The digital gauge will allow Tori to match the bite force of the human jaw, around 170 pounds.
Ow, hurts.
Time to put the artificial jaws to the test. Tori applies pressure. Maybe too much.
What's that? Busted a tooth.
Busted a tooth? Melted, and then can I heard it go over here somewhere?
You shouldn't eat hard candy.
This is a job for teeth of steel.
I'm about to cut some canine.
Tori shapes some steel rods into bite-sized chunks and shapes them on a grinder. They might not get you a Hollywood contract, but these iron choppers will be able to replicate the bite force of a human mouth.
I finished the teeth. I hope they work.
Meanwhile, the microwave is getting a workout.
Look at this. The one light green layer in the middle there started to bubble, and nothing else did. I'm gonna put this piece back in there without the core in the middle of it and see whether it just kind of pools and nothing else happens.
Okay.
Christine uses an infrared thermometer to measure the temperature of the candy's molten inner core.
225 degrees.
Yeah, I went up to 225.
Well, you know, this is actually pretty interesting because it's clear that it is reacting in that layer a lot more than the surrounding areas. And that's where we get some kind of an explosion. Ow, really retains the heat. You could get seriously burned with this. In fact, I think I did.
Want to get me a jawbreaker to test?
The jawbreaker is packing heat. Now to apply pressure.
All right, that's a full bite. Nothing's going on.
They try again, but the jawbreaker just won't crack. Perhaps the candy has been heated too fast.
Defrost cycle. See if we can figure it out on this machine. Okay, so
You could do, I think it might be power level 1. Oh,
All they have to do is figure out how to program the microwave.
it's too smart.
0.1 pound. That's probably a good bet.
We don't have the manual for this anywhere.
Probably somewhere, but I think that's sort of what it does.
30 years of special effects experience finally pays off.
There we go. Start. That was crazy. It's like watching paint dry.
But even after so much persistence and patience, there's no busting this rock-hard candy. They test combination after combination of heating, cooling, and pressure until finally,
Going hot on the candy.
Okay. Everybody clear?
Ready?
Yeah. And 3, 2, 1.
Ice water over here.
I got it on my arm.
a good reason to never let your guard down. Christine's been hit in the face.
I got burned by the candy. I wasn't wearing a face mask like I should have been. And I couldn't protect myself with my hands.
Upwards of 225 degrees, and with high heat retention, the sticky liquid candy is extremely painful.
I'm okay. I've got first-hand experience, though. Doesn't feel good. It got the side of my neck and my temple, so it hurts.
The MythBusters have conclusively proven that heating a jawbreaker and applying pressure can be a big myth take.
I mean, if you were a 5-year-old kid and this went off in your face, there's no doubt it would leave serious burns on you. It was very, I mean, I could feel it like 10 seconds, 15 seconds later. It wasn't cooling down. It's like napalm.
It's myth confirmed. Next up, Carrie and Grant are hot-footing it to Sonora, California, to begin answering a burning question.
We're here to observe an actual firewalking class being put on by the Firewalking Institute of Research and Education.
They want to test the myth, is walking on hot coals a case of mind over matter? Or is there some other reason feet don't get fried? Setup to light up takes just over an hour, and tensions are rising along with the temperature.
Getting a top of about 1,300 Fahrenheit.
Carrie's convinced that what matters is not what's on your mind, but how hellishly hot the coals are.
After measuring this fire at 1,400 degrees and hearing that after they rake it out, it only is going to go down to about 1,000, there's absolutely nothing so far that's convinced me that I'm going to walk on this.
But that's not stopping anyone else. The students glide across in a zen-like zone without a single injury. But before the team follows in their footsteps, they want some hard data.
I've seen it done, but I'd like to have a little bit more scientific backing before I'm willing to risk my feet.
And that means cooking up an experiment back at the workshop. To find out how much heat gets to the feet, Carrie begins by fabricating a foot from heat-resistant silicone, while Tori starts prepping the firewalk.
First, what we're gonna do is we're gonna lay down 30 feet of sod. That way we don't crack our cement. Then what we're gonna do is lay down 20 feet of wood. We're gonna light that wood on fire, let it burn down, and start walking. All right, we got fire extinguisher standing by.
Got a hose standing by.
Let's do it.
Now that we have our fire lit, we'll wait 1 hour for it to get to the optimal temperature for fire walking. That's when the coals are just glowing red and we can smush them down so we have a nice flat surface to walk on.
As the wood burns down, Grant works on a sensor for the fake feet.
So this is called a copper slug calorimeter. And the idea is that you have this disc of copper that's an exact size and weight. And based on those characteristics and its thermal transfer, you can connect a thermocouple to it, which measures temperature. You'll be able to predict whether or not you're going to get first, second, or possibly even third-degree burn.
And with the fake feet screwed to the bottom of Carrie's shoes, there's no more excuses.
Oh, I feel just like Cinderella.
All right, you guys, it's over 1,000 degrees, which is what we saw at the firewalk. You ready to go?
Yeah. Oh, yeah, I see the coals glowing.
Okay, go ahead.
While Carrie crunches the coals, Grant crunches the numbers.
Yeah!
See, that wasn't so bad.
No.
All right, Grant, what'd you get?
I got some really interesting results.
The first set of results up for analysis is the high-speed camera shots, showing exactly how much toe-touching time there is.
So it turns out that my foot was only in contact with the hot coals from heel to toe for 9/10 of a second. And my full weight was only on it for 5/10 of a second. So right there, it shows you that might be one of the reasons that you don't get burned when you walk across hot coals, is you're not touching the coals for very long.
And what about the temperature?
The interesting thing is that we don't predict any injury, first, second, or third-degree burns, during a normal walk. So as long as she keeps moving, theoretically, you won't get burned.
Charcoal and ash are better insulators than wood, so the top side of the coal should be relatively cool.
So in theory, you should be able to pick up one of these coals, which on one side is 900 degrees, and on the charcoal and ashy side, it's 300 degrees. So I should be able to put this in the palm of my hand without injury, and potentially light a fire. Here we go. Ha. There you go.
So firewalkers experience bearable temperatures due to the speed they walk, the low conductivity of charcoal, and the insulation from the ash. It's not looking good for mind over matter. But now, it's time to test the temperature with real Tootsies.
All right, those coals are all red hot. You guys ready?
There's no turning back now.
Oh! Are you nervous at all?
No.
A little.
All right.
After a few minutes of psych up, Carrie's first into the foot fryer. Cue dramatic music.
It's not totally not hot.
Next up on the charcoal catwalk, Grant.
Yeah, Grant!
As cool as a cucumber, he glides over it.
Yeah!
Very graceful!
There we go. A little hotter than I expected, but I think I made it.
And that just leaves Tori, who charges in without hesitation.
Go, Tori!
Here we go.
It's not that bad at all. I thought it was gonna be a lot worse than that. It looks way worse than it is. It's really not that bad. It's the mental part that messes with you the most. In fact, I didn't even feel it. I had to walk back one more time just to see whether or not they were hot.
It seems that physics stop your feet from being flame grilled, not mind over matter. But what about a mind unprepared? To find out, let's segue to the next day.
What are you cooking? We're gonna be cooking, well, at the bottom of your feet.
We're looking at the science of firewalking.
Firewalking! Awesome!
Adam is hot to trot until the moment of truth.
It's one thing to think intellectually that I've always wanted to walk on fire. It's quite another to feel the heat of 2,000 some odd degrees at my back.
But now, it's time for Adam's trial by fire.
You can do it. All right, so is the ambulance ready? You gotta tell your feet.
My heart rate just went up a bit. Okay.
He knows nothing about the data or the technique. Will he get across unscathed?
Yeah, all right, here we go.
Apparently not.
Wow! That hurt a lot. Ow was going through my head. As I did it, walk, 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 this isn't so bad. Holy crap, this is pretty bad. Ah! Like that. That's about the thought process.
So it seems that it does matter what's in your mind, but only insofar as knowledge about technique and preparation go.
With no prep at all, I think I made a classic mistake of speeding up and digging my feet into the coals more.
High-speed analysis shows Adam's hard marching method meant some of the coals stuck to his feet, giving them more of a chance to conduct the heat. So science still wins. This myth is busted. Next, it's fire meets fire extinguisher. According to our fans, the myth goes something like this. If you fling a fire extinguisher into a fire, the heat builds up pressure in the tank until it ruptures. Then all the retardant spills out and douses the fire. Or does it? Sounds dangerous. But Tori's got fireside safety covered.
So what's gonna happen is I'm gonna stick my fire extinguisher up here like this. So I hit the quick release, and the fire extinguisher goes in the fire. For my next trick, I will vanish in thin air. I wave the magic wand.
The crew have been transported to the Alameda bomb range, and they're going to put the torch to 3 different types of fire extinguisher.
The myth that a fire extinguisher can fall into a fire and extinguish the entire fire is sort of general. It doesn't tell what kind of fire extinguisher. So we went and got every single kind we could. We have water, we have carbon dioxide, and we have chemical foam. One of these might work.
They prep the fire for the most common type of fire extinguisher, CO2. Fire needs 3 things to burn: oxygen, fuel, and heat. Remove one, and the chain reaction fizzles out, which is exactly how CO2 works. Because it's heavier than oxygen, it blankets the flames, replacing oxygen, and the fire triangle collapses. But if you chuck a full CO2 canister into a fire, could it actually explode and put the fire out?
Now this one is under the most pressure, 800 PSI, but it's probably the least likely to explode because it has a pressure release valve, and this prevents it from exploding.
And Carrie's sure it will be a fizzer.
There is no way a fire extinguisher is going to fail so catastrophically that it explodes and then extinguishes the fire.
But for safety's sake, Carrie and Grant hunker in the bunker while Tori performs the crash and dash.
That's it. Ready? You ready?
Run, Tori, run!
Get inside.
Tori just has time to get his breath back before the hot canister busts a leak.
It sounds like something's hissing.
Yeah, the safety valve released.
And 15 minutes later, it's empty. The safety valve has done its job.
It's a good testament to the safety feature that's built in there. It's designed in an overpressure situation, such as raising temperature, to vent all the CO2 safely. As far as this myth goes, it's busted for the CO2.
This experiment may have been a fizzer, but how about a water extinguisher? Unlike the CO2 tank at 800 PSI, the water extinguisher has much less pressure at only 100 PSI. But it has no safety valve. Even so, Carrie's got major doubts.
Even if there's a rupture, I don't see the fire going out. This is a big fire, and I just don't think that there's going to be enough explosion to put it out completely.
All right, so the fire is ready. So this is water extinguisher.
All right, let's do it.
In 3, 2, 1.
At over 1,000 degrees, the burning coals rapidly convert the water inside the tank to steam under ever-increasing pressure. And 5 minutes in,
Oh, look, it's ruptured. It's actually spraying out water right now.
but at that rate, the water won't be putting out this big fire.
No explosion, no fire going out.
No. In fact, right now, that's not any more effective on the fire than, like a tea kettle.
Yeah.
But don't underestimate steam power.
Cool! Yeah. We almost took out the thermal camera.
It actually came at us.
Obviously, the tank didn't vent the steam fast enough. And when the pressure got too much, something had to give.
Now, it didn't explode or put out the fire, but it did turn into a little rocket. And the whole can, flipped over, and then it went straight at us.
But as far as the myth goes,
So far, this myth is looking busted.
that's 2 in the busted bin. But next in the firing line is the foam extinguisher.
This is for Class B fires, which is flammable liquids like solvents or oils or that sort of thing. Tanks rated for 300 PSI, but just like water, they only fill it to 100 PSI. We're gonna throw this in the fire, see if it explodes and extinguishes it.
And just like the water-filled tank, it has no safety valve.
Okay. We're ready. I think the fill valve will be the first thing to go. It'll hiss out. And potentially, we could have another mini missile. But as far as explosion goes, I don't think so. Here we go. Foam extinguisher in 3, 2, 1. We got 9 minutes before the last one blew.
You guys bring cards?
Let's do charades.
Okay, you first.
Okay.
2
words.
I get you.
Sounds like.
And put out the fire! It exploded and put out the fire!
Oh my God!
It's spraying!
Oh, it's rain.
Oh, God!
Yep, the foam-filled canister blew the fire into the next county.
That was awesome!
Where's the canister?
I don't know, but it definitely exploded and it put out the fire. Wouldn't you agree?
Something happened all right, but not exactly what the myth described. It wasn't the chemicals that put out the fire,
Put out the fire!
but the explosion that scattered the fuel to far-flung corners of the field. But as for the chemical foam extinguisher, this myth is still plausible.
Oh, yeah. I'd say there's still a few embers, but it is plausible at least.
Oh, definitely plausible. Look at that. That could put out a fire.
All right, maybe this isn't the safest way to put out a fire, but it put out a fire.
Oh, I love it when I'm wrong. I was totally wrong. I thought nothing was gonna happen.
With the flames extinguished, it's time to bring the temperature down for 3 frozen myths. In our first story, can a padlock be broken by freezing it?
Yeah, I've seen that on TV, like MacGyver or Burn Notice. They spray liquid nitrogen into a lock, and then they can shatter it with a gun butt or a hammer.
Well, this sounds pretty simple to test. We'll just set up some locks. We'll try to break in with the regular burglar kit, and then we'll try to break in using liquid nitrogen, and we'll see which one's faster.
What is a regular burglar kit?
You know, like crowbars, hammers, stuff like that. You guys don't have a burglar kit?
No.
No.
Oh.
Liquid nitrogen, or LN2, is a fluid with a temperature of around minus 196 degrees Celsius, or minus 321 degrees Fahrenheit. It's almost impossibly cool, but can it freeze a lock? Tori is going to start with a control test. Just a padlock at room temperature versus a hammer and crowbar.
Okay, control padlock.
3, 2, 1.
Woohoo!
4 seconds.
That's the reference point. Now to find out what difference soaking the lock in liquid nitrogen will make.
So liquid nitrogen, very dangerous. You gotta suit up first.
So we're on to test 2, which is the liquid nitrogen part of this test. We're going to pour liquid nitrogen directly on the lock and let it soak for a few minutes so it gets good and frozen, and then Tori's gonna give it the same bash that he gave the control lock.
Okay, hose is off.
Personally, I'm hoping for some sort of cartoon-like shatter here.
In 3, 2, 1.
Okay. Look at that. 1 second. I see we made a difference with the liquid nitrogen.
That is cool. Tori hit it with 1 shot, and it shattered in less than a second.
So it's looking good for the myth. But considering the padlock was so easy to break, even without the LN2, the team wants a tougher challenge.
All right, if anybody needs me, I'll be in my office.
For that, they want a deadbolt. And as before, Tori is first going to smash through for a control comparison.
This always reminds me of elementary school.
School of Hard Knocks?
So I broke through the deadbolt using the pick and the sledgehammer,
Tick-tock, buddy. Cops are on their way.
but it took me 5.5 minutes. It was very hard, and it was very loud.
There you go.
Pretty sure somebody would have called the cops.
Go, go, go! Okay.
5 minutes and 37 seconds for the control. Now let's soak it in liquid nitrogen and see if you can blast through that lock faster.
With a full 4 minutes exposure to liquid nitrogen's mind-boggling minus 321 degrees Fahrenheit, the lock is ready for our not-so-subtle burglar.
In 3, 2, 1. Oh my gosh!
That's incredible! One shot and the lock already broke.
Keep going, keep going.
Oh my God, that's hilarious.
Why is liquid nitrogen making it easier to break these locks? Well, all metal has a ductility to it, which means if I smash this lock with a hammer, it's going to deform the metal. Whereas if I introduce the liquid nitrogen to the lock, we are going to lower the temperature, causing all the particles that are in constant motion to slow down, removing energy, making it brittle, so that if I now smash it with a hammer, it's actually going to shatter.
Nice.
That is incredible.
What's
1
the time?
minute, 4 seconds.
That is way less than half your time.
One shot and the lock shattered.
Oh yeah.
That is so cool.
Cool, for sure. And the evidence is stacking up in favor of this freezing fable. But the team isn't satisfied just yet.
Okay, that small padlock was totally ridiculous. It was actually not that hard to break, even without the liquid nitrogen.
Yeah, I think we need something that gives us a bigger difference between liquid nitrogen and no liquid nitrogen.
Maybe something like this?
I love it.
So with the giant padlock secured to the bunker, Tori gets stuck in.
Man, this lock's a lot harder.
But even after 4 minutes of solid pounding with a sledgehammer, it's not the lock that breaks,
Come on, John Henry, you can beat it.
but the bunker.
I broke the handle of the bunker. The lock is still locked. Now, we asked for a beefier lock, and let's face it, we got it.
Yeah.
That still works.
But we're not gonna stop there. Now we're gonna try liquid nitrogen on the same exact kind of lock and see if that gives us the edge that we need.
Okay.
This time, the guys apply their LN2 for a full 5 minutes before Tori unleashes hell. And incredibly, after just 5 meaty blows, they're in.
We're gonna 14 seconds.
It's a massive result. On one hand, 4 minutes of failure. On the other, 14 seconds to success.
You guys, I can't believe it. Adding liquid nitrogen to a lock actually makes it easy to break. This myth is totally confirmed.
I know, and I just can't believe how big of a difference it made using the liquid nitrogen.
Wait, did we just give our audience a guide to making breaking and entering easier?
Yeah, pretty cool, huh?
Yeah, okay, that did occur to me, but this is a difficult technique to use. 1, you need to carry around a thermally isolated vat of liquid nitrogen. 2, you need a large amount of safety equipment. 3, you need to apply it to the lock for at least 5 minutes. And 4, you need 3 people to pull it off. Yes, it's successful, but you know what? It's not the most subtle technique out there.
Yeah, I agree. It's probably not gonna catch on.
You know what, though? This myth is still confirmed.
Confirmed.
For our next myth, Adam and Jamie are mixing fire and ice.
All right, dude, this one's about thermite, and I think you'll like it.
What is it?
All right, these two guys, they take a bucket of thermite, they put it on a bunch of blocks of ice, and they light it with a fuse, and it doesn't just burn like we've seen thermite burn. The whole friggin' thing explodes.
Thermite is metal powder and metal oxide. It burns at ferociously high temperatures, which you'd think would just make ice melt. Instead, according to the myth, the ice will explode.
Let's head out to the bomb range and try it out.
Before they test the myth, Jamie wants to warm up with a demonstration of just how hot thermite burns.
What we're building first is a kind of pagoda from bricks and steel plates. The idea is to see how many plates the thermite burns through once it's ignited.
Thermite's a mix of fine metallic powders, but the ideal ratio is debatable. Of course, we want the best burn for our buck, so this should be a great way to bench test Jamie's special blend. With the thermite inside a bucket, Jamie throws in 2 matchbooks attached to a fuse.
Okay, this is thermite penetration test. In 3, 2, 1.
With the fuse lit, it's only a matter of time before thermite's full power is unleashed. The thermal imaging camera should enhance the experience.
I've always wanted to see this thing in action just like this.
As far as I know, it's never been done before. I mean, you see what happens after the fact, but we're going to see the whole thing all at once.
There we go.
1, 2, 3.
Nice!
Oh. 4 plates.
Right, the top 1 and 3 down. That was pretty cool.
It was.
It's the opposite of cool. At 4,000 degrees Fahrenheit, the burn is too bright to view at close quarters. It's a major meltdown.
We can hang these up in a gallery and we'll make it like $1 million.
If it melts metal, it's definitely going to have an effect on ice. But will it really result in an explosive hail of ice cubes? Someone order 10 one-pound ice blocks? Ah, that'll be the MythBusters.
10 blocks of ice. We'll go get the thermite.
They stack the ice on a bed of bricks.
This is thermite and ice in 3, 2, 1. We're good.
Needless to say, never try this yourself. We've got all the safety gear, the expertise, and the blast screen.
This is killing me. Don't tell me. What the heck?
Don't you hate it when you're huddled behind a blast screen with a nervous bunch of grown men and nothing happens?
I think it's a dud.
Finally, Jamie can take it no more. Fully fireproofed, he fashions a new fuse and takes a furtive walk, knowing the old fuse could blow at any time.
So Jamie's put on the full fire suit to protect himself to replace another fuse and matches because, well, we don't know. He could touch that bucket and it could all go off. So it's a little bit touch and go right now.
Jamie wastes no time setting the new spark.
He's lit it.
Let's hope it stays lit. This experiment should confirm or bust the myth of exploding ice.
That looks like the match is going off. There it goes.
I'd say that was an explosion.
I'm pretty sure that qualifies.
And Adams found the source of that thunk that shook the blast screen.
In the popular parlance, we call this piece of ice a hunter-killer because it went all the way from ground zero to our blast chamber. Luckily, it is
Ice-proof.
Some chunks of ice flew as far as 150 feet. The brick pallet is a smoldering ruin, and there's no trace at all of the galvanized steel bucket.
Look at that. That tells the whole story right there.
It shot the bricks right down through the bottom of the floor there. That was a bona fide explosion.
But what actually made the ice go boom? The truth is, no one really knows.
Experts I've talked to are speculating that heat from the burning thermite is decomposing the water into hydrogen and oxygen, which in the presence of a source of ignition, namely hot thermite, is exploding. Now, I sort of have a problem with that because that requires that a whole bunch of hydrogen and oxygen be instantaneously created, and I don't know that that's possible. There is another explanation, I'm just speculating, and that is that something in this reaction is aerosolizing all the thermite. It's, you know, the steam or something is throwing all this powder up into a cloud of thermite, and that's exploding. We don't know. It's a mystery, but one way or another, that was a heck of a bang.
A bang big enough to call this one confirmed. For our final story, we'll need to order more liquid nitrogen.
All right, exploding frozen tree. Let's talk about that one.
Okay, well, the story goes that there was a leak in a liquid nitrogen processing plant. One of the pipes burst, and liquid nitrogen started to flood down into the office.
Now, it was the holidays, so there was a Christmas tree and a bunch of decorations, but most importantly, the liquid nitrogen leaked onto the Christmas tree.
And bang, it explodes into splinters.
Right, now, in theory, this could work. I mean, maybe the water inside of the tree froze and expanded and caused the tree to fail catastrophically.
Just like us mammals, most of the mass of a tree is water. When water turns to ice, it expands. And if the freezing is almost instantaneous, well, it doesn't take a tree surgeon to see how that might just ruin Christmas for everyone.
So where should we start?
Well, let's start by finding out how much water a tree contains. We can do a classic biology dry weight experiment.
All right, well, once we've determined that, let's get two identical trees. We'll take them out to the bomb range. We'll blow one up as a control, and the other one we'll pour tons of liquid nitrogen over and see what happens.
Sounds like fun. Let's do it.
Our wood chipper's here.
Step one is to see just how much H2O lurks inside a standard Christmas tree. And this will not be pretty.
We're gonna shake the dirt off this, throw this thing into a wood chipper, and then we're gonna take all those wood chips, throw them in pans, measure their weight. After that, we're gonna stick them in a low heat kiln, slowly dry them out, evaporate all the moisture out of them, and then measure them again.
So instead of trimming the tree, they'll tear it to shreds. But every last leaf and twig must be preserved for science.
So what we want to do is capture every little bit of the tree that comes out of the wood chipper.
You sure are chipper today.
And just in case some shards of shrubbery miss the trash can, there's a safety net.
I think we'll be able to catch everything with this.
It's just crazy enough to work.
Now, welcome to a true Christmas nightmare. As the tree is shredded and every part collected in a bucket, in a horrifying act that would make even the Grinch grimace.
Awesome.
I have to say, this is definitely one of the better smelling experiments we've ever had in the shop. Mmm, so much better than rotting meat.
Oh, wait till you smell it when it comes out of the oven.
I know.
It's gonna be delicious.
Fresh pine scent.
What started out as mulch looks like being the dish of the day.
So we've taken our 6-foot Christmas tree, put it through a wood chipper, and distributed it onto 8 baking trays. Over time, as the water bakes out of the tree, that weight's gonna go down until at some point it will plateau. Then we know we've gotten all the moisture out, and that will tell us what the overall moisture content of the tree was. 7.2 pounds.
They'll check the diminishing mass each and every hour until it stabilizes.
Tray number 1, 7.4 pounds.
All right, 7.4, that's it. The oven is filled. Now it's time to bake our tree.
In the meantime, they have a date at the bomb range with another ill-fated tree.
I hate to get sappy here, but does anybody feel really bad about blowing up a tree?
Oh.
Smells great.
Now, of course, we can all imagine what an exploding tree looks like, but in the name of science and all things cool, we're gonna do it anyway.
Without beating around the bush, they need a true tree explosion as a point of comparison.
What do we got here?
Little deck cord, that ought to do it.
Yeah.
Yeah, we could use C4, we could use all sorts of explosives, but I think det cord gives us the best chance of not blowing it up to complete smithereen.
Yeah, that's probably a good call. And look, it's gonna look like a Christmas tree.
The team retreats as the bomb tech sets the firing cap, then calls in the chaos.
Fire in a hole! Fire in a hole! Fire in a hole!
All right, so this is liquid nitrogen exploding tree control test.
Still calling this a control test.
Wait, you're acting like I am enjoying this. This is serious science right now, okay?
All right.
In 3, 2, 1, go, JD!
Oh! It looks like we just gave it a haircut.
And then some. This is the kind of defoliation they hope to get from a big fat blast of LN2.
Dang, look at that tree all over the place.
That's great. That's pretty much what I expected to see.
Many trees were planted to replace those we blew up, and now they know what an exploding tree looks like.
Test liquid nitrogen.
All right.
Before they apply the LN2, it's back to the shop to check on how plausible the myth is. Is there even enough water in the tree to possibly cause it to blow up when frozen?
So our figures have finally plateaued, and what's left of the tree is now 33% of its original weight.
What?
Wow, that is a lot of water.
Tree's 2/3 water.
So there might actually be something to this myth.
All right, well, let's get some fresh trees, go out to the Alameda bomb range, pour some liquid nitrogen over them, see what happens.
All right.
Awesome.
If you say so. Meet tree number 3 and a truckload of the same stuff they used to break the padlock.
Anybody who's taken a high school chemistry class knows just how effective liquid nitrogen can be to freeze something. So we thought in MythBusters fashion, we'd take a small quantity, like 2,800 gallons of liquid nitrogen, and we're gonna pump it through this hose.
And out through these phase separators, where it'll separate the liquid nitrogen from the gases. So we'll be able to dump hundreds of gallons of liquid nitrogen over the entire tree.
And just to check our progress, we've got this temperature probe, which should be good down to minus 300 degrees Fahrenheit. We'll jam it in the trunk and watch it remotely.
Winter is coming, and it's going to be harsher than any you've ever seen.
Do I think we're gonna get an explosion? I have my doubts. I do think we might see some cracking, some splitting of the tree. But you know what? There's always that little chance that that tree could explode. I mean, we have been wrong before on MythBusters.
I have my doubts that this tree is going to give us any sort of grand explosion. If anything, maybe some of the ornaments might explode, which, you know, when I told the story later, I might say the tree exploded. But I'm definitely standing behind the blast shields, just in case I'm wrong, because I am often wrong.
Like an extremely isolated new ice age, the liquid nitrogen engulfs the tree. As the liquid turns to gas, oxygen gets sucked out of the mix, and the team brace for a truly bubble-blowing blast.
43.5 degrees.
That's dropping fast. That's like 20 degrees in 2 minutes.
It's dropping faster now.
What are we at?
16.2, heading towards 0.
This thing could explode at any moment.
It sure could. And let's note that the freezing point of water is 32 degrees Fahrenheit.
Dropping really fast now. Minus 90, minus 95.
What?
Minus 100.
Antarctica cold.
Yeah.
This tree is definitely frozen.
It's at minus 140 now. It's minus 150.
How much time has elapsed?
We are now at 7 minutes.
The LN2 dissipates slightly in the breeze, but the temperature of the tree continues to plummet.
We're dumping gallons and gallons of liquid nitrogen over the top of the tree. It looks like fog rolling down off the top of it. You can actually see the trunk slowly turn white and freeze.
No tree in history ever got this chilly this fast. The coldest temperature recorded on Earth is minus 146 degrees Fahrenheit. And this freeze shows no sign of slowing.
We're reaching minus 200.
I can't even comprehend that.
Over the next few minutes, the tree gets much colder, pushing onto the limits of absolute zero. But still, no explosion.
We got the core temperature of the tree to minus 330 degrees Fahrenheit. If that tree were going to explode as a result of the water inside freezing, it would have. But unfortunately for the myth, it's still intact. Look, it's been almost half an hour, over 200 gallons of liquid nitrogen. I think we should call this and check it out.
All right, let's call it. All right, go ahead and kill the liquid nitrogen.
They couldn't get it any colder, and the tree hasn't so much as shed a leaf.
You know what? I was really hoping this thing was gonna explode.
Check for cracks.
Wow. Not any cracks, though?
No
I don't
cracks.
see any cracks at all.
But the whole trunk is like covered in frost. It means it's completely been covered in liquid nitrogen.
What should we do now?
Well, I wonder what would happen if there was some sort of impact. Could you actually shatter this tree the way you do with those science experiments?
Yeah, how about if we hit it with the shotgun?
That sounds like a plan to me.
A hammer blow worked for shattering the locks earlier, so maybe a load of buckshot will do the job here.
If anybody loves Christmas, turn your heads now. This just seems wrong, shooting a Christmas tree. Safety's off. Here we go in 3, 2, 1.
The tree takes the hits, but it's still not smashing to smithereens.
All right.
It's about as good as we get.
What more can you do?
Well, here's what you could have done much earlier. Asked an expert.
As an arborist, what are we doing wrong? Why is the tree not exploding?
Trees in colder climates are naturally built to not explode. What happens is the water inside of the tree cells moves to air spaces outside of the tree cells, and those air spaces provide enough room for the water to expand without exploding the tree.
So the water does freeze and it does expand, but because of the air spaces, the trunk doesn't go boom, boom.
Correct.
So no matter how much we freeze this tree, it's never gonna explode?
I doubt it.
Stupid adapting nature.
Time to admit they were barking up the wrong tree.
Look at that. It's obvious that this tree is frozen completely to the core, and even with a high-velocity impact, it did not shatter it or do anything that looked like an explosion.
Yeah, we froze it with liquid nitrogen, didn't explode. And we hit it with a shotgun shell, still didn't explode.
All right, I guess we're calling this one busted.
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 You know, I could always go into the tree trimming business.